Welcome to our comprehensive exploration of gluconeogenesis. This vital metabolic pathway allows our body to produce glucose from non-carbohydrate sources, ensuring a steady supply of glucose even when dietary intake is limited. Today, we'll delve into the intricate details of this process. Importance of gluconeogenesis. Gluconeogenesis is crucial for maintaining blood glucose levels, particularly during fasting, prolonged exercise, or when a low-carbohydrate diet is followed. The liver is the primary site of gluconeogenesis, with the kidneys playing a secondary role. This process helps ensure that glucose is available for tissues, particularly the brain, which relies heavily on glucose. Key precursors. The main precursors for gluconeogenesis include lactate. Produced by anaerobic glycolysis in muscles, it is transported to the liver where it is converted back into glucose. Pyruvate. A central metabolite from glycolysis and amino acid metabolism, it serves as a key starting point for gluconeogenesis. Glycerol. Released from the breakdown of triglycerides in adipose tissue, it can be converted into glucose. Amino acids, particularly alanine and glutamine, which can be converted into intermediates that enter the gluconeogenic pathway. The gluconeogenic pathway. Let's follow the step-by-step process of gluconeogenesis, which mirrors glycolysis but with unique enzymes to bypass the irreversible steps. Step 1. Pyruvate to phosphoenolpyruvate. Gluconeogenesis begins with pyruvate, which is first converted to oxaloacetate in the mitochondria by the enzyme pyruvate carboxylase. This reaction requires ATP and bicarbonate. Oxaloacetate is then transported to the cytoplasm and converted to phosphoenolpyruvate by phosphoenolpyruvate carboxygenase, a reaction that requires GTP. Step 2. Phosphoenolpyruvate to fructose-16-bisphosphate. Phosphoenolpyruvate is then converted through a series of steps to fructose-16-bisphosphate. This series involves the enzymes enolase, pyruvate kinase, and others, replicating the reverse of glycolysis but with different intermediates and regulators. Step 3. Fructose-16-bisphosphate to fructose-6-phosphate. Fructose-16-bisphosphate is converted to fructose-6-phosphate by fructose-16-bisphosphatase. This step is crucial as it bypasses the phosphofructokinase 1 step of glycolysis, which is irreversible. Step 4. Fructose-6-phosphate to glucose-6-phosphate. Fructose-6-phosphate is then converted to glucose-6-phosphate by the enzyme phosphoglucose isomerase. This step is part of the gluconeogenic pathway that aligns closely with glycolysis. Step 5. Glucose-6-phosphate to glucose. Finally, glucose-6-phosphate is converted to glucose by glucose-6-phosphatase. This step is essential as it allows glucose to be released into the bloodstream. Clinical relevance. Disruptions in gluconeogenesis can lead to significant metabolic issues. Impaired gluconeogenesis may result in hypoglycemia, while excessive gluconeogenesis can worsen hyperglycemia in diabetes. A thorough understanding of this pathway is essential for effective management of these conditions. Conclusion. In conclusion, gluconeogenesis is a complex yet essential process that generates glucose from non-carbohydrate sources. By grasping its mechanisms and regulation, we gain crucial insights into metabolic health and the management of related diseases. Thank you for joining us in exploring gluconeogenesis. We hope this overview has deepened your understanding of this vital metabolic pathway.